Hello everyone, I'm Javier Cifuentes-Faura from the University of Murcia in Spain. It's an honor to participate in this conference as a keynote speaker. Thank you very much to the organization for inviting me. Today we will present a literature review on an interesting topic related to mathematics and the pandemic. The lecture is entitled Mathematical Modeling as an Epidemiological Tool to Enhance Modeling of the Social and Economic Impact of the Pandemic. Faced with a global pandemic, many researchers have tried to respond to all the issues and the social and economic impacts generated. They tend to collect data and develop models, algorithms, or analytical tools that allow for a deeper understanding of the underlying factors. In this way, results can be obtained that help decision makers to enact certain policies over others. Mathematical modeling has served as an epidemiological tool to explain this type of phenomenon. From SARS to, more recently, COVID-19 or SARS-CoV-2, many studies have attempted to provide answers to the evolution and characteristics of epidemics. These mathematical models allow researchers to understand the dynamics of epidemics and are useful for determining the strategies to follow and control policies. They also serve to better understand the system and prevent future epidemics, determine prevalence and incidence, and make objective decisions. Building mathematical models for the study of a pandemic caused by an infectious disease will help to understand the spread of an infectious disease through the population under different scenarios, extract properties and characteristics of the relationship between the variables analyzed, or predict the consequence of introducing specific changes. There are two types of mathematical models, deterministic and stochastic models. In a deterministic model, it is possible to control all of the factors involved in the analysis of the phenomenon and to accurately predict its results. In a stochastic model, it is not possible to control all of the factors that intervene in the progress of the phenomenon, so the results are neither unique nor exact, but its outcome will occur with a certain probability. In the epidemiological context, in a deterministic mathematical model, a single individual can cause a generalized epidemic, whereas in a stochastic mathematical model, it is possible that the disease does not evolve in the population and the epidemic dies out. Epidemiological models usually assume that individuals are in one of several possible states, and depending on that state, the population is categorized into different categories: susceptible, infected, or removed individuals, among others. The most important models are SI, SIS, SIR, and SACEIR, which can be represented by a deterministic or stochastic model. With the recent COVID-19 pandemic, attempts have also been made to explain the structure of the underlying virus, how it spreads, prevention measures, containment, and diagnostic protocols. The vast majority of papers have employed the SIR model to predict the spread of the pandemic or the number of COVID-19 cases. The use of mathematical models for the study of infectious disease should be used with caution, since it is difficult to understand a complex problem without performing minimum modeling, although it is not always possible to model the totality of real situations. Discrete time models, or difference equations, are used to formulate some epidemic models such as SI, SIS, SIR, or ACE-EIR. Continuous approximation of these models are more frequently used in modeling situations as a consequence of their mathematical manageability. Different equations do not perform as well as their continuous approximations. Denoting by S the susceptible population, individuals without immunity to the infectious agent who can be infected, and by I, the infected population, the discrete time epidemic SI model has the following formulation. In order to ensure that the solutions are positive, a necessary and sufficient condition is the one that appears in the screen. The analogous differential system has the following form. The discrete model for the standard SIR model divides the population into three compartments: susceptible, infectious, and recovery, although the latter states may include death or infective isolation. The SIR model aims to predict the number of people who are susceptible to infection, actively infected, or have recovered from infection at a given point in time. The SIS model is another of the most widely used mathematical epidemiological models to emulate epidemics, which is obtained by iterative computation. It is assumed that in a closed society there are no deaths, no births, and no population migration, and infected individuals are not reinfected after recovery. Clearly, these assumptions are valid for a limited time interval. In the SI model, over the course of the pandemic, almost everyone eventually becomes infected. In the SIS model, each individual belongs either to the susceptible set or to the infected set. Some infections do not confer immunity. These infections do not have a recovery state, and individuals become susceptible again after infection. This type of disease can be explained by the SIS model. Individuals who are cured do not develop permanent immunity as in the SIR model, but are immediately susceptible to the disease. The SIS model moves individuals from the infectious class to the susceptible class, and therefore there is no eliminated class. The model adopts the following expression. The three models, SI, SIS, and SIR, can be derived as special cases of the SIRS model. These models are quite simple, so they are easy to calculate, although sometimes they oversimplify complex epidemiological processes. For example, if one wants to take into account the time between the moment when an individual is exposed to a disease and the moment when that individual becomes infected and contagious, as in the case of coronavirus 19 disease, it is necessary to make some modification, such as that offered by the SEIR model. E denotes exposed but not yet contagious. Generalizations have been made based on these models, including births, deaths, migration, vaccination, and treatment. More complex models have been developed by taking into consideration spatial aspects to understand how the mobility of population migration affects the spatial distribution of the disease, and that contacts are made through individual interactions. Network models describe a population and its interaction with the nodes vertices of the network representing individual and the edge links representing interaction between individuals that could lead to transmission of infection. Disease dynamics in networks can be determined by modification of the equations of the main epidemiological models. Based on the information provided by the Web of Science database, an exploratory descriptive investigation was carried out using the techniques and tools of bibliometric analysis of scientific production on epidemiological network models, describing how certain fields of research are related and how they evolve over time. This is one of the world's most important databases of bibliographic reference and citation of periodicals that provides analysis tools to evaluate the scientific quality of publications. It also offers one of the best-known quality indicators, the Journal Citation Reports, which is used by organizations that evaluate research activity. Given the importance of this topic, no time restrictions were included, obtaining all documents up to 30 October 2021. Several researches were performed combining different keywords: model, network, epidemic, analysis, control, and network model. Some of this combination result in a very small number of papers, and others included many papers that were unrelated to this research. The following combination of keywords was chosen: network model, epidemic, and analysis, resulting in a total of 244 papers. We selected papers that were articles, including review articles. The result was 212 papers. A preliminary reading of the abstract was performed initially, followed by a more exhaustive reading of each article to verify that it met the established inclusion criteria. For example, we discard papers that, although they have these keywords, use them only to globally situate their analysis. After this filtering, 145 documents were obtained. The distribution of the keywords of the analysis paper is shown in the figure. The most important keywords are, in addition to those used in the Web of Science search, disease, transmission, spreading, and modeling. In the bibliometric analysis carried out on the 145 articles obtained with the filters introduced, all of the publications were examined by relating them to the epidemiological models existing in the literature, together with a study of the citations. The number of publications per year is shown in the figure. Of the 145 papers selected, most have been published in the last decade. In the last 10 years, the trend increased until 2015. In the last 3 years of the period analyzed, 41 papers with impact have been published until October 2021. Although the contribution to the literature on epidemiological mathematical models in networks come from researchers from 36 different countries, there is an important geographical imbalance. China stands out with 25%, America represents 23%, those from England represent 7%, Canada represents 6%, and the rest of the countries are represented with percentage lower than 5%. There are 491 different authors in the publication presented. The majority, almost 80%, have only one article. The authors with the most published articles are listed in this table, shown in the screen. The author with the most articles, 5, is Zheng Jin of North University of China. Only 8.97% of the papers were signed by a single author. 20% were signed by 2 authors. 3 authors signed 25% of the papers. 17% were signed by 4 authors, and the rest were signed by 5 or more researchers. All of the results are until the end of 2021. It's important to remember that. The journals in which the papers analyzed were published are different. A total of 87 different journals were found, plus one stand out with 8 publications. This journal is multidisciplinary and accepts research from different areas, such as science, engineering, medicine, and the related social science and humanities. With 5 papers each, we find the Journal of Mathematical Biology, whose main aim is to identify and work with mathematical models derived from biological knowledge. The Journal of the Royal Society Interface, which publishes research that applies, among other disciplines, Mathematics and Physics to Biological and Medical Science, and the Journal of Theoretical Biology and Physical Review, in which priority is given to biological aspects over mathematical ones. Most of the journals are located in the first quartiles, and many of them belong to quartile 1, such as Applied Mathematical Modeling or Advances in Difference Equations. This table shows the research areas of the different journals. As can be seen, areas that stand out are mathematics, with 14.83% of papers, and science, technology, other topics, with 13%, followed by mathematical computational biology, life science, biomedicine, other topics, and physics. The research coming from these areas includes new methods and mathematical models, both from theoretical and applied points of view, which address calculating the probability of transmission of an epidemic, how to control the transmission, control measures, prevention, etc. The epidemiological models used in the studies are diverse, with the SIS, susceptible infected susceptible model, serving as the basis for 36 studies, the SIR, susceptible infected recovered, with 27, and the SEIR, susceptible exposed infected removed, with 12. Other less commonly used models are susceptible exposed infected in quarantine or recovered, and susceptible exposed asymptomatic infected symptomatic recovered. Regarding the type of epidemic analyzed in different studies, these have been classified into three areas: epidemic of infection diseases and invasive species, epidemics transmitted through social networks, internet, rumor spreading, and epidemics in general. It should be noted that some of the models of rumor dissemination are different from those of epidemiology. Publications analyzing the spread of infectious disease epidemics are predominant, accounting for nearly 60% of the papers analyzed. The lowest percentage, 9%, correspond to articles whose epidemiological study focus on social networks or the spread of rumors. Of the papers published up to the time of data collection, in the final of 2021, there are 21 research papers focusing on the current pandemic caused by the COVID-19. Of the publications analyzed, 42% are papers in which theoretical models were developed with extensive mathematical demonstration based on the epidemiological models used in the existing literature. 46% of the cases are theoretical but do not include demonstration, and only 11% of the articles are applications of the epidemiological models. To forecast the evolution of an epidemic, model approaches include the simulation of the dynamics of disease transmission and recovery or the empirical fitting of data trends. Epidemiological models used to perform exhaustive mathematical demonstration are more frequently in articles on epidemics in general than in the rest, and those based on practical exercises are more frequently on epidemics of infectious diseases. The citations of our work show its importance in the scientific community and its contribution, although this depends on other factors that can condition the dissemination of the work, such as the prestige of the author, the topicality of the subject, or the journal in which it's published. The 145 papers collected have a total of 2,416 citations in the period analyzed. This number has been growing exponentially. The most cited article of those examined, with an average annual citation count of 30.2, is titled "Spread of Zika virus in the Americas" and was written in 2017 by Sang et al., who performed a simulation of the spatial and temporal dynamics of the Zika virus epidemic in the Americas, providing probability distribution for the timing and location of Zika introduction in Brazil, the estimated attack rate, the timing of the epidemic in the affected countries, and the projected number of newborns born to Zika-infected women. Next, there is the work conducted by Kraft in 2015, Infectious Disease Transmission and Contact Networks in Wildlife and Livestock, which reaches on average 20 citations per year, and in which transmission dynamics in wildlife and livestock populations are studied, analyzing the mismatch between the contact networks measured in animal behavior and the relevant parasites in those networks. The papers are mainly cited in 8 journals, although in total they are found more than 1,000 journals. PLOS ONE has 5.70% of the citation, followed by Scientific Report and Physica A. And now we go with the conclusion on this important review. Modeling the dynamics of epidemics is essential to project their evolution through simulation and provide useful information for designing disease control and prevention strategies. The models help to determine the role of factors such as the mechanisms of infection, total population variation, and population movement in disease transmission dynamics. Using the keywords network model, epidemic, and analysis, we search the Web of Science database to discover what research has been published on network epidemiological modeling, who the most relevant authors are, and in which journal it is published. After an exhaustive review of each of the papers obtained in this research, the number of papers selected was 145, published from 2001 to October 2021. It was found that great efforts have been made to consider the dynamics of diffusion in epidemiology, predominantly using the susceptible infected susceptible (SIS) and susceptible infected removed (SIR) models. In addition, simple models such as SI and more complex models such as SEIR, which also includes the E for exposed, have been used. The number of publications on the subject has grown in recent years. There are 491 authors with journal citation report publication in this field of research from various disciplines, and almost 50% come from China and the United States. The author with the most articles is Shen Jin from North University, China. The journals in which most articles are published are very well placed in the rankings, belonging to the Q1 and Q2 quartiles. A large number of papers focus on disease involved in infectious disease epidemics, and just over 14% focus on the current pandemic caused by COVID-19, representing almost 50% of the papers in 2020 and 2021. The most cited papers are Zhang et al., who performed a simulation of the spatial and temporal dynamics of the Zika virus, and Kraft in 2015, in which transmission dynamics in wild animals and livestock population are studied. PLOS ONE stands out as the journal with the highest number of citations for this paper. The epidemiological models used in these studies are diverse, with the SIS model serving as the basis for 36 studies. The use of epidemiological models in the related literature has resulted in very relevant publications, which suggest that factors such as the mechanism of infection, total population variation, and population movement play an important role in disease transmission dynamics and therefore provide useful information for strategies designed for disease control and prevention. And this is the end of the presentation. Thank you so much for your attention. If you have any doubt, do not hesitate to contact me. You can see my email on the screen. Thank you.